Okay, very good. We are here to do the practical exercise, okay, and see how we can build our first RSM model in Minitab. So the initial steps, I come again, is you go to start, DOE, response surface, create design, and then you choose bus backend because we are focusing on bus backend since we have data for bus backend that we have already published in one or two other journals. So I'm going to use that as a case study to learn bus backend design and how we reported it. Okay. So the next is you define the number of factors, levels, or range. Then you had your center point for robustness, randomize, and generate the design. Okay. So the data is already dropped in the community. So let's just come pick our data at table 3. This is what we're going to be following to generate the bus backend. So now let's go. So you go to start, then you go to DOE, then response. Can you see response? Then you come to create response surface design. So here you check bus backend, then continuous factors 5. Okay. Then you come here. Okay, define, come to this design. So our center point, we leave it at 6. Okay, most of the time is good. If you have 5 factors, you can use 6 center point. If you have 4 factors, you use 5 center point. If you have 3 factors, you use 4 center point. So you must use it's good to use a +1 center point for your factors. That is helping you to contain the error and then to see the consistency in when you are reproducing the data. Okay, so center point means that you have the same experiment. Maybe 6 center points. So you have the same experiment 6 times to see if the value will be the same or close to each other to check the deviation and error. So we use that also to create lack of fit. Okay, when you are doing your analysis. All right. So when we are talking about lack of fit, please refer back to this center point. All right. Good. So then you come to factors. So in these factors now we can now put the information in this table A to E, and then you can see them here. Let me just copy very fast. So now let's see the high and low now. I want to paste the high and low. I'll just let me see if I can paste it like this. Okay. So let me see if I can paste it like that. So good. So it's pasted. Then you okay it. Okay. Then we come to options to randomize. You can leave it there, randomize. Then you come to results. Okay, so we want everything. All right. Then I think after that you did what? You do what? Generate. Okay, you can see what it gives me. Okay. So this is 46 runs, 5 factors, and 6 center points. Okay. So let me show us the runs. Can you see it? All right. So let me compare it with the data I have here. If it's the same, because I've done this work before. All right. Because it's randomized, so it's not exactly the same. All right. Can we see? Can we see? So it's not exactly the same. Okay. So this is starting from 15, starting from 15, 3, 2, 5, 50. This one is, let me check it. This is starting from 10. So it's randomized. So what we can do is we can just paste the data. So after I did experiment based on these runs, then I got these values. All right. So I got these values. Okay. Then paste it there. Okay. So what you do is you paste this here. So you say W, X, Y, the same W, X, Y, Z we have been talking about since. So W, X, Y, Z. Okay. So then you paste your information. Copy. Can you see? So when you paste the data, okay, you can trim it. Okay, so everything is trimmed. Then you start coming here to do your what? To do your
Samuel,
analysis. So you come here,
put that.
you click DOE, response, and then Mrs. Afola Shade, thank you, ma. Please help us to mute. Then you click analyze response surface. Okay. Now this data is randomized against this very thing that was generated. So I cannot use it directly. So if I had used an unrandomized data and I have it arranged in the same order, then I can use it. Okay. So, but it's just exactly what we have done. So I'll just quickly use it that way, show you a little of what it can bring. Then I show you the result I got at my publication, and then we'll explain some things for us. So, to do it, you can come here and do your responses. What are our responses? We have W, W, X, Y, Z. Okay. So we have so that's it. Then you come here to check the graph. Okay, so you check all of this. That's the way we did it before. Then you come here to check the options. All right, so options are okay. Come here to check the results. Change to extended tables. Then you come here, storage. You pick all of this. Can you see? Pick all of this. All right, then okay it. Then is there another thing? Check results. It's fine. Okay, so the next thing is now to okay. So when you okay, you will see your response, okay, regression done for you using bus vector. So these are, you can see it's similar to the full factor factorial. Okay. You can see you have all of these, but the data will not be regular because it was the response that I pasted on the randomized data are not arranged. Do you get? They are not arranged. So you can see all of the stuff is bringing. These are the stuff that you need. Then when it comes to analyzing it one by one, you can then now come here to get your surface plot, contour plot. Can you see all of this? All right. So your surface plot, you can just say I want to plot my Z, and then I'm choosing mass of this against mass of that. Okay. And then you can just check the contour, use default, contour lines, symbolic, you pick everything, and then you can check your options. Here you can put your title. You can say contour plot for, you can say what's the value? You can say Z, Z. Okay, so then so then you view the model. This is the model. You close it, then you okay it. So then the contour plot will come out. This is the contour plot. Okay, and this contour plot is just showing you the relationship when you plot Z. Okay, and then you have mass of glycerin here, and you can look at it, and you have mass of starch here. Okay, so this is the relationship. So this is showing you the Okay, so this is showing you based on the data you have, this is showing you the optimized points that you may want to fit your stuff around. So this is also one of the maximum points here. Okay, you have at 20, then you have that. This is another point. Okay, so that's counterpoint for Z. You can also go and plot counterpoint, counterpoint for other, okay, other parameters. Just select it. Can you see? Y, Z, W, whatever you want. Okay. Apart from the counterpoint, you can also do surface plot. Okay, so let's go. Surface plot. You come here and you click it. So let's do surface plot for Z and let's see what it will give us. Before you do that, you can go to setting to check that your settings are in order. This is the minimum. This is the average of the values, okay, for your factors, okay. Then this is the, you put the title here, surface plot of Z. And then here you can view the model. Then here you, let's see options. So you okay it to see the contour plot. Can you see the contour point here? Sorry, can you see the surface plot? This is surface plot. They're like Mr. Audi asked the other time, you can always edit this graph. You can always double click it on it and then you type. Just that way, very easy. Copy on this, just type, very easy. All right, so and you can drag them, okay, down, especially to maybe you want to screenshot them together. You can screen grab like this, and then you can just screen grab, screen grab using light shot or sniper tools. So you can copy and paste them on your on your and paste them on your Word document and then you report them. Okay. So quickly, let's see how this same table were used to report in a journal that's Green Energy and Environmental Technology Journal, Intech Open Journal in London. You can see the same experimental design. Okay, this is the factors, and this is the response. This response, W to Z, our energy consumed, weight of plastic, tensile strength, elongation, and then you can see these are just our writing to see that they are functions of all the 5 factors: mass of glycerin, mass of this, volume of that, and time. And then this is what we are expecting to give us in our variable. We wrote this after we have seen what we got. All right. So, but before we see what we got, we use this table to generate these experimental runs. We generate these experimental runs up to this place. And these experimental runs, we got this response from each of the sample. This is energy, this is weight, this is tensile, and this elongation. And after that, we did the surface plot, just like I showed you there. Surface plot of, this is surface plot for energy. Energy is W there. So W, you can see W. And then I brought down the legend, okay, and the title so that I can screen grab it and paste it here together. So this is showing us how the energy increased, energy consumed increased with respect to the mass of starch used and the volume of glycerin consumed. Okay, and then we also saw the surface plot for the weight of bioplastic, how it's increased according to the increasing parameters that were used. Okay, so here we saw the different surface plots. Okay, then we also have contour plots, but for this report, we did not paste any of the contour plots because contour plots are just a 2D relationship, while surface plots are 3D. Okay, so surface plot enable you to see more interactions, okay, in 3D, in you see more factors combining together, while contour plot is just 2D. So this is the composite generability for us to see how all the parameters blended together and then give us an optimum points. Okay, so how did I do that? I just came here. Let me bring the data for this experiment. Okay, good. So this is the data for that material, for that article. So we're looking at so you can see each of these response were copied. You can see the regression, the R square is 99.901 and adjusted R square is 98 point something percent. So they are very close to each other and also close to 100%. So that means that this model is very good. You can see the ANOVA table. So you can see the p-value. The p-value here are less than 0.05. So that means that they are good to go. But for the one that are more than that, this one is 1. That means I will ignore the value. In fact, the value are even already 0. So I'm not going to use them. So I will only pick the ones that are, the values are less than 0.05. Okay. So for the composite variability, you can come here, come to stats, and then you come to GOE, base, and then you optimize. So when you want to optimize, just come here, and then you select. Okay, so here you decide what you want to optimize. So here I'm doing this according to this. We are doing A, B, C to D, choosing the factors. Are we following? Are we following? Hello?
Hello, we are following, sir.
Okay, very good. So I was explaining how I got to this place. This is you run
Don't put it in.
you run optimal point for all the factors that you have looking at, and then you now start changing. So yes, so this table is for the ANOVA for the energy consumed. So also the other factors also have their own table. Okay, so you can collect all the tables. Okay, and then you put them here like this. Now this is for efficient estimate for energy consumed. This is the this statistics for the energy consumed. So here, I think I now collected all the P statistics for each of the response, energy consumed, tensile, elongation, and weight, and then put them all together so that I can summarize it. Okay. So here is summary of the lack of fit, analysis of other responses. So all the lack of fit in each of the responses, I collect them together and then put them here, summarize them here. Okay. And then this place is the predictive model. So when you generate your response, you receive a model for each of the response. Okay, like this now. Let me come to response for this one. You can see that there's a model here. Can you see this is the model here? So regression equation in uncoded factors or coded units. So this model, you can collect it and put it here. Okay, your for whatever factors that you have generated it for. I think it's for so you have that, and then that's for x. So this is for y. This is for y. You can see the equation here. So you collect it. This is for y, and then this is for think w. Okay, this is another one. This is for energy consumed. I think I use that here for energy consumed. Okay, you can see it. Energy consumed minus 1,399, blah blah, like that. So that's what you have here. Okay, this is the regression equation. Okay, and I was talking about to know this which factor is. They can see so much here, so much long equation here, but some of these factor here are insignificant. Like I see this one, this is 0.00 times a, or blah 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 like that. So that one you may not need to add it to your equation. That's why you see that my equation is very smooth and short here. So I was able to remove those ones that are zeros and those ones that their p factor are more than 0.05. So I did not add them to the equation. Okay. So that's why you have it as neat as this. Okay. So then I give it for others like that. And then summarize my optimized response condition. So here, whatever I've gotten as my optimized response prediction, which is here, I have to go and rerun it in the lab. After running it in the lab, then generate this response for it. Okay. After you response for it, then run my, standard error fit, run my percentage, 95% confidence level, and my other factors. Then come here to, okay, this is sum of error of it. So here, there is a validation analysis of the optimum value. That means after running this experiment for this optimum point, then we run all the analysis and then check with the statistics, is synthesized, and check the deviation, the error, and the standard deviation. So that is to see how to validate the analysis. Okay. All right. So before we now then bring out our conclusion. So how do you conclude, or how do you respond? How do you report this information we have gotten from your experiment and your DOE? That's what we're going to be looking at in the next video. So, okay. So multi-response surface for real-world decision making. In real life, problems often involve multiple competitive objectives. So this section focuses on balancing trade-off, e.g. high topic acceptance or low cost. Okay, using variability functions to combine multiple responses, exploring compromise solutions acceptable to stakeholders or decision makers. So case study, like now, maybe a municipal government wants to maximize compositing rate or minimize waste collection cost, okay, or they want to maintain odor level below threshold. Minitab helps to find the best combination of factors to satisfy all criteria simultaneously. Okay, so participants will practice assigning weights and important levels to each response. Then you find the best global solution based on overall reliability. Okay, so, so that's what you do. So at the end of the experiment, you're able to perform residual and model diagnostic checks to validate your RSM models, just like I did for my experiment. After I got the optimum, then I come back to rerun the experiment and then to validate it. So you're able to conduct your confirmation runs to test model predictions. So use miniature response optimizers for single and multiple response goals. So the next section, okay, which is the final one, we explore communicating insights and integrating validated models into impactful scientific and policy communication. So I'm interested in the data communication and policy translation. So the objective is to equip participants with the skills to convert statistical findings into compelling, actionable insight for scientific publications and policy making. So why sophisticated tools like DOE, RSM are powerful? Okay, their impact depends largely on how the results are communicated. Okay, so participants will learn how to move from numeric output to meaningful narratives. E.g., you emphasize on cause and effect relationships supported by data, saying that increasing X leads to 50% improvement in Y. Okay, we prioritize relevant and practical results over complex statistics for decision makers. You avoid misinterpretations or overstatements, e.g., you have p-values misuse or over reliance on R square. So this is how to manage them. When you see a p-value that is really, really, really higher than 0.05, you don't use it at all. So you avoid that. Okay. And then when you see R square showing you almost 100%, and the p-value is still very bad, then you still ignore it. So this technique helps you to avoid just looking at only how to the R square is high. So you combine these two factors. All right. So example, rather than saying the model is R square equals to 89, so you say the model reliably explain 89% of the variation in recycling rates based on campaign frequency and policy incentives. That's how you report it. Okay. So you don't report like a mathematician, you report like a communicator. All right. So you also use visual and tabular presentation, which enhance understanding and trust. Okay. So we'll look at how to do that. So best practice for use clean and interpretable tables, just like Mr. Oji has submitted. Those tables are very clean. All right. And also, as I've shown you, how to pick the key variables and results using your mean, using your p-values. Okay, use footnotes to explain statistical terms. Some people might not understand what the p-values or confidence level or C high. When you say C high, you go down and say key. C high means confidence intervals. Okay, so that's what you do, and then you use your chart properly. You can edit your plots, you edit your bar charts, you edit your axis, surface plot. So you choosing the right visual format for the audience, whether they are scientific, policy, or public, is very key. So the tip I'm going to leave us with is that always label axis clearly, use appropriate colors, and include legend when needed. All right. So participants will be introduced to the structure and tone of precise policy brief that leverages statistical insights. Right. Okay, so the key component here is you need to have the executive summary